We are familiar with many elements or molecules which are neither shining, malleable, nor ductile like metals. Then what are they? They are nonmetals. The nonmetals exist in all three states, that is, solid, liquid, and gaseous. However, most nonmetals are either solids or gases. Bromine is the only nonmetal which is a liquid. In the periodic table, the nonmetals are present on the right-hand side. You have seen in the earlier modules that magnesium burns in air with a dazzling white flame. Do all the metals react in the same manner? Almost all metals combine with oxygen to form metal oxides. The reaction being metal plus oxygen gives metal oxide. For example, when copper is heated in air, it combines with oxygen to form copper oxide, a black oxide. The reaction being 2Cu plus O2 gives 2CuO. Similarly, aluminium forms aluminium oxide. The reaction being 4Al plus 3O2 gives 2Al2O3. Recall from earlier modules how copper oxide reacts with hydrochloric acid. We have learned that metal oxides are basic in nature. But some metal oxides, such as aluminium oxide, zinc oxide, etc., show both acidic as well as basic behavior. Such metal oxides, which react with both acids as well as bases to produce salts and water, are known as amphoteric oxides. Aluminium oxide reacts in the following manner with acids and bases. The reaction being Al2O3 plus 6HCl gives 2AlCl3 plus 3H2O. Al2O3 plus 2NaOH gives 2NaAlO2, sodium aluminate plus H2O. Burnt in air, Part 2. Most metal oxides are insoluble in water, but some of these dissolve in water to form alkalis. Sodium oxide and potassium oxide dissolve in water to produce alkalis as follows. The reaction being Na2O solid plus H2O liquid gives 2NaOH aqueous. K2O S plus H2O L gives 2KOH aqu. It is important to remember that all metals do not react with oxygen at the same rate. Different metals show different reactivities towards oxygen. Metals such as potassium and sodium react so vigorously that they catch fire if kept in the open. Hence, to protect them and to prevent accidental fires, they are kept immersed in kerosene oil. At ordinary temperature, the surfaces of metals such as magnesium, aluminium, zinc, lead, etc. are covered with a thin layer of oxide. The protective oxide layer prevents the metals from further oxidation. Iron does not burn on heating. but iron filings burn vigorously when sprinkled in the flame of the burner. Copper does not burn, but the hot metal is coated with a black-colored layer of copper 2 oxide. Silver and gold do not react with oxygen even at high temperatures. It is important to remember that sodium is the most reactive of the samples of metals taken here. The reaction of magnesium is less vigorous, implying that it is not as reactive as sodium. But burning in oxygen does not help us to decide about the reactivity of zinc, iron, copper, or lead. Let us see some more reactions to arrive at a conclusion about the order of reactivity of these metals. With water, metals react with water and produce a metal oxide and hydrogen gas. Metal oxides that are soluble in water dissolve in it to further form metal hydroxide. The reaction being metal plus water gives metal oxide plus hydrogen. Metal oxide plus water gives metal hydroxide. But all metals do not react with water. Metals like potassium and sodium react violently with cold water. In case of sodium and potassium, the reaction is so violent and exothermic that the evolved hydrogen immediately catches fire. The reaction being 2K solid plus 2H2O liquid gives 2KOH aqueous plus H2 gas plus heat energy. 2Na solid plus 2H2O liquid gives 2NaOH aqueous plus H2 gas plus heat energy. The reaction of calcium with water is less violent. The heat evolved is not sufficient for the hydrogen to catch fire. Ca solid plus 2H2O liquid gives CaOH2 aqueous plus H2 gas. Calcium starts floating because the bubbles of hydrogen gas formed stick to the surface of the metal. Magnesium does not react with cold water. It reacts with hot water to form magnesium hydroxide and hydrogen. It also starts floating due to the bubbles of hydrogen gas sticking to its surface. Metals like aluminium, iron, and zinc do not react either with cold or hot water, but they react with steam to form the metal oxide and hydrogen. The reaction being 2Al solid plus 3H2O gas gives Al2O3 solid plus 3H2 gas. 3Fe solid plus 4H2O gas gives Fe3O4 solid plus 4H2 gas. It is important to remember that metals such as lead, copper, silver, and gold do not react with water at all. You have already learned that metals react with acids to give a salt and hydrogen gas. That is, the reaction being metal plus dilute acid gives salt plus hydrogen. However, this is not a generalized case. Hydrogen gas is not evolved when a metal reacts with nitric acid. It is because HNO3 is a strong oxidizing agent. It oxidizes the H2 produced to water and itself gets reduced to any of the nitrogen oxides N2O, NO, NO2, etc. But magnesium or Mg and manganese or Mn react with the very dilute HNO3 to evolve H2 gas. Also, the rate of reaction with dilute acid differs from acid to acid. If we allow to react Mg, Al, Zn, Fe with dilute HCl, we find that the rate of formation of H2 bubbles is fastest in the case of magnesium. This reaction is also the most exothermic in this case. The reactivity decreases in the order Mg is more than Al, is more than Zn, is more than Fe. In case of copper, no bubbles are seen and the temperature also remains unchanged. This shows that copper does not react with dilute HCl. How do metals react with solutions of other metal salts? As an important rule, it should be remembered that reactive metals can displace less reactive metals from their compounds in solution or molten form. We have seen in the previous modules that all metals are not equally reactive. We checked the reactivity of various metals with oxygen, water, and acids. But all metals do not react with these reagents. So we were not able to put all the metal samples we had collected in decreasing order of their reactivity. Displacement reactions studied in Chapter 1 give better evidence about the reactivity of metals. It is simple and easy. If metal A displaces metal B from its solution, it is more reactive than B. The reaction being metal A plus salt solution of B gives salt solution of A plus metal B. The reactivity series. The reactivity series is a list of metals arranged in the order of their decreasing activities. After performing displacement experiments, the following series, known as the reactivity or activity series, has been developed. Here you can see potassium is the most reactive among the metals, with gold being the least reactive of the metals. It is simple and easy. If metal A displaces metal B from its solution, it is more reactive than B and is placed higher in the reactivity series. In the previous activities, you saw the reactions of metals with a number of reagents. Why do metals react in this manner? Let us recall what we learned about the electronic configuration of elements in class 9. We learned that noble gases, which have a completely filled valence shell, show little chemical activity. We therefore explain the reactivity of elements as a tendency to attain a completely filled valence shell. Let us have a look at the electronic configuration of noble gases and some metals and nonmetals. We can see from this table that a sodium atom has one electron in its outermost shell. If it loses the electron from its M shell, then its L shell now becomes the outermost shell, and that has a stable octet. The nucleus of this atom still has 11 protons, but the number of electrons has become 10. So there is a net positive charge giving us a sodium cation, Na+. On the other hand, chlorine has 7 electrons in its outermost shell, and it requires one more electron to complete its octet. If sodium and chlorine were to react, the electron lost by sodium could be taken up by chlorine. Sodium loses one electron to form sodium plus ion. Chlorine accepts that electron to form chlorine minus ion. After gaining an electron, the chlorine atom gets a unit negative charge. Because its nucleus has 17 protons and there are 18 electrons in its K, L, and M shells. This gives us a chloride anion, Cl-. Sodium and chloride ions, being oppositely charged, attract each other and are held by strong electrostatic forces of attraction to exist as sodium chloride or NaCl. It should be noted that sodium chloride does not exist as molecules but aggregates of oppositely charged ions. Let us see the formation of one more ionic compound, magnesium chloride. Here, magnesium loses 2 electrons to form Mg2+ ions. Chlorine accepts electrons to form chlorine ions. Oppositely charged magnesium and chlorine ions join together to form MgCl2 compound. The compounds formed in this manner by the transfer of electrons from a metal to a non-metal are known as ionic compounds or electrovalent compounds. The Earth's crust is a major source of metals. Seawater also contains some soluble salts, such as sodium chloride, magnesium chloride, etc. The elements or compounds which occur naturally in the Earth's crust are known as minerals. At some places, minerals contain a very high percentage of a particular metal, and the metal can be profitably extracted from it. These minerals are called ores. Extraction of metals. You have learned about the reactivity series of metals. Having this knowledge, you can easily understand how a metal is extracted from its ore. Some metals are found in the Earth's crust in the free state. The metals at the bottom of the activity series are the least reactive. They are often found in a free state. For example, gold, silver, platinum, and copper are found in the free state. Some are found in the form of their compounds. Copper and silver are also found in the combined state as their sulfide or oxide ores. The metals at the top of the activity series K, Na, Ca, Mg, and Al are so reactive that they are never found in nature as free elements. The metals in the middle of the activity series Zn, Fe, Pb, etc. are moderately reactive. They are found in the Earth's crust mainly as oxides, sulfides, or carbonates. You will find that the ores of many metals are oxides. This is because oxygen is a very reactive element and is very abundant on the Earth. Thus, on the basis of reactivity, we can group the metals into the following three categories. 1. Metals of low reactivity. 2. Metals of medium reactivity. 3. Metals of high reactivity. Different techniques are to be used for obtaining the metals following in each category. Several steps are involved in the extraction of pure metals from ores. Let us understand these steps in detail. Enrichment of ores. Ores mined from the earth are usually contaminated with large impurities such as soil, sand, etc., called GAN. The impurities must be removed from the ore prior to the extraction of the metal. The processes used for removing the GAN from the ore are based on the differences between the physical or chemical properties of the GAN and the ore. Different separation techniques are accordingly employed. Extracting metals low in the activity series. Metals low in the activity series are very unreactive. The oxides of these metals can be reduced to metals by heating alone. For example, cinnabar or HGS is an ore of mercury. When it is heated in air, it is first converted into mercuric oxide or HgO. Mercuric oxide is then reduced to mercury on further heating. Similarly, copper, which is found as Cu2S in nature, can be obtained from its ore by just heating in the air. The metals in the middle of the activity series, such as zinc, iron, lead, copper, etc., are moderately reactive. These are usually present as sulfides or carbonates in nature. It is easier to obtain a metal from its oxide as compared to its sulfides and carbonates. Therefore, prior to reduction, the metal sulfides and carbonates must be converted into metal oxides. The sulfide ores are converted into oxides by heating strongly in the presence of excess air. This process is known as roasting. The carbonate ores are changed into oxides by heating strongly in limited air. This process is known as calcination. The chemical reaction that takes place during roasting and calcination of zinc ores can be shown as follows. During roasting, the following reaction takes place. 2ZnS solid plus 3O2 gas on heating gives 2ZnO solid plus 2SO2 gas. During calcination, the following reaction takes place. ZnCO3 solid on heating gives ZnO solid plus CO2 gas. The metal oxides are then reduced to the corresponding metals by using suitable reducing agents such as carbon. For example, when zinc oxide is heated with carbon, it is reduced to metallic zinc. ZnO solid plus C solid gives Zn solid plus CO gas. You are already familiar with the process of oxidation and reduction explained in the earlier modules. Obtaining metals from their compounds is also a reduction process. Besides using carbon or coke to reduce metal oxides to metals, sometimes displacement reactions can also be used. The highly reactive metals such as sodium, calcium, aluminium, etc. are used as reducing agents because they can displace metals of lower reactivity from their compounds. For example, when manganese dioxide is heated with aluminium powder, the following reaction takes place. 3MnO2 solid plus 4Al solid gives 3Mn liquid plus 2Al2O3 solid plus heat. These displacement reactions are highly exothermic. The amount of heat evolved is so large that the metals are produced in the molten state. In fact, the reaction of iron 3 oxide, Fe2O3 with aluminium is used to join railway tracks or cracked machine parts. This reaction is known as the Thermit reaction. The reaction being Fe2O3 solid plus 2Al solid gives 2Fe liquid plus Al2O3 solid plus heat. The metals high up in the reactivity series are very reactive. They cannot be obtained from their compounds by heating with carbon. For example, carbon cannot reduce the oxides of sodium, magnesium, calcium, aluminium, etc. to the respective metals. This is because these metals have more affinity for oxygen than carbon. These metals are obtained by electrolytic reduction. For example, sodium, magnesium, and calcium are obtained by electrolysis of their molten chlorides. The metals are deposited at the cathode or the negatively charged electrode, whereas chlorine is liberated at the anode or the positively charged electrode. The reactions are: at cathode, Na plus plus E minus gives Na At anode, 2Cl- gives Cl2 plus 2E-. Refining of metals. It is very important to remember that the metals produced by various reduction processes described above are not very pure. They contain impurities which must be removed to obtain pure metals. The most widely used method for refining impure metals is electrolytic refining. Many metals such as copper, zinc, tin, nickel, silver, gold, etc. are refined electrolytically. In this process, the impure metal is made the anode. And a thin strip of pure metal is made the cathode. A solution of the metal salt is used as an electrolyte. The apparatus is set up as shown. On passing the current through the electrolyte, the pure metal from the anode dissolves into the electrolyte. An equivalent amount of pure metal from the electrolyte is deposited on the cathode. The soluble impurities go into the solution, whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. When a metal is attacked by substances around it, such as moisture, acids, etc., it is said to corrode, and this process is called corrosion. Silver articles become black after some time when exposed to air because they react with sulfur in the air to form a coating of silver sulfide on the surface of silver article. Copper reacts with moist carbon dioxide in the air and slowly loses its shiny brown surface and acquires a green coat. This green substance is called rust. Iron, when exposed to moist air for a long time, acquires a coating of a brown flaky substance. This brown flaky substance is known as rust. Now we will learn about the conditions under which iron rusts. Take 3 test tubes. Place clean iron nails in each of them. Label them A, B, C. Pour some water in the test tube A and cork it. Pour boiled distilled water in test tube B. Add about 1 ml of oil and cork it. The oil will float on the surface of water and prevent the air from dissolving in water. Put some calcium chloride in test tube C and cork it. Calcium chloride will absorb the moisture, if any, from the air in the test tube. Leave the test tube for few days. What do you observe? You will observe that iron nails rust in test tube A but not in test tube B and C. In test tube A, the nails are exposed to both air and water. In test tube B, nails are exposed to only water but not air. In test tube C, nails are exposed to dry air but not moisture. This shows that conditions under which iron rusts are availability of water, availability of oxygen. Rusting of iron can be prevented by painting, oiling, greasing, galvanizing, chrome plating, anodizing, or making alloy. Alloy is a homogeneous mixture of two or more metals or of a metal and a non-metal mixed in fixed proportion by mass in their molten states. Alloying is a very good method of improving the properties of a metal. We can achieve the desired properties by using this method. For example, iron is the most widely used metal, but it is never used in its pure state because it is very soft and easily stretchable when hot. But if iron is mixed with a small amount of carbon, then it becomes hard and strong. When iron is mixed with nickel and chromium, we get stainless steel, which is hard and does not rust. Similarly, pure gold, that is 24-karat gold, is very soft and hence is not suitable for making jewelry. So, it is alloyed with silver and copper to make it hard. Alloy of the metal mercury is called as amalgam. Copper is a good conductor of electricity, but when mixed with zinc to form brass or mixed with tin to form bronze, it loses its conducting property. An alloy of lead and tin, which is called as solder, has a low melting point and is thereby used for welding electrical wires together.